All right, so when you're trying to find the domain of a rational function, one way to go about it, which I recommend, is just to determine the values that x cannot be. So a lot of the cases, it'll be finding values that make the denominator equal to 0. So a value for x that makes 4x plus 1 equal to 0. Now, the reason for that is because you can't divide by 0, so any value that makes this equal to 0 will not allow the equation, to work. It would be undefined. So we solve this, take away 1, divide by 4, and we'll get x is equal to negative 1/4. So this is what we don't want x to be. So our domain is basically, you could say all real numbers except negative 1/4. Now, same idea for 2. We would set 2x plus 4 equal to 0. Solve this. And we get x is equal to negative 4 divided by negative. So we would say that our domain are all the values except negative 2. So all real numbers make sure you write all real numbers. Most teachers are okay with this, but don't just put x can't be negative 2, because sometimes it's not clear enough if you really understand what's going on. Okay, so same idea here, except we're going to look at the denominator being factored. So we would have x squared minus 3x minus 18, set that equal to 0. We factor that. That would be equal to x minus 6 times x plus 3. Solving this, you would have x minus 6 equals 0, so then x is 6, and then x is negative 3. So again, we don't want x to be 6, and we don't want x to be negative 3, because plugging those values in will make the denominator equal to 0. So again, we could write all real numbers except negative 3 and 6. All right, number 4. Okay, so we have y equals 2 to the 2 minus x over x. Now, don't let this, expression fool you, because you can actually take a number and raise it to any, positive or negative number, and it doesn't actually matter. So we don't have to worry about the denominator. Again, we just don't want the numerator, we don't have to worry about the numerator. We just want to make sure that the denominator is not 0. And this is pretty, simple. It's just that x can't be 0. So again, we would just write all real numbers except 0. Okay, so here we have 2 square roots, the square root of x minus 3 minus the square root of x plus 3. So we would basically set x minus 3 to be greater than or equal to 0, because remember, we can't take the square root of a negative number, and at least so that we could stay in the real numbers. And so same thing we hear, x minus 3 is greater than or equal to 0, and x plus 3 is greater than or equal to 0. Solving this, we would get x is greater than or equal to 3. And solving this, we would get x is greater than or equal to negative 3. Now, we don't just, we can't just say this one, or, we can't just, we have to think actually which one would make sense. The domain would be x is greater than or equal to negative 3, because if we say x is greater than or equal, the domain would be strictly this one, because if we said that the domain was x is greater than or equal to negative 3, that means we could plug in like negative 2 and 0, and if we did, that would make this a negative number, and that wouldn't work. So we have to make sure the domain works for both of them. So the domain is just, all numbers greater than or equal to 3. All right, here we would, again, look for this expression 2x minus 9 to be greater than or equal to 0, because again we can't take square roots of negative numbers. But we also don't want the denominator to be 0, so we would have 2x plus 9 is not equal to 0. We wouldn't want this to be equal to 0. So we would solve both of these and then combine, the domains into a way that makes sense. So adding 9, dividing by 2, we would want x to be greater than or equal to 9 halves. This one would be x can't be negative 9 halves. Now, again, this doesn't matter because we have to have x be greater than, 9 halves or 4.5. So this is, that automatic, if it's greater than 9, or if it's greater than 4.5, it's automatically not going to be, negative 9 halves. The domain we could just have is this interval. All numbers greater than or equal to 9 halves as their domain. All right, the numerator is fine. We can, take any number and plug it into there. Now the denominator, we're taking the 4th root of x plus 5. Now, let's remember what the 4th root means. All that means is what number to the 4th power will give you this. So what number can you take the 4th root of? And that just means, well, we have to think. We can only take 4th root of numbers that are positive, or 0. So we would have to make x plus 5 greater than or equal to 0, similar to like square roots. So we solve this. X take away 5, x is greater than or equal to negative 5, and that's it. Problem 8. Again, we can only take the square root of numbers 0 or greater, so we would solve x squared minus 5x minus 14 for the 0. Or let's actually just put this has to be greater than or equal to 0. Make it more clear. Now this is going to be a little more involved, so let's factor this and let's see what we got to do. Because if we factor this, it'd be x minus 7 times x plus 2 is greater than or equal to 0. Now let's think a bit. If in order for a number to be, positive, either they both have to be positive or they both have to be negative. So either this has to be positive and that has to be positive, or this has to be negative and this has to be negative. If they're opposites, then this number will be negative, or this quantity will be negative. So let's kind of mess around with some potential factors, some potential numbers that we can multiply to gain some understanding of how this would work. My technique is solve for the zeros of each of these. So we would solve for x minus 7 is equal to 0 and x plus 2 is equal to 0. The zeros here would be negative 2 and 7. Now the reason I advise solving for the zeros is because then you can check numbers in this region, and in this region to see what product will give you a positive or negative value. So for example, let's say if we picked a number over here, let's say we picked like negative 5. If we plug negative 5 into here, we would get negative 12 times a negative 3, and that would be a positive number. So any numbers in this region will be positive, and that's okay. That's what we want. So this would be part of our domain. And since it could be 0 as well, we were going to include negative 2. Now we're going to check a number in here. Let's have x is 0 and see what happens. If we plug 0 into here, we would get negative 7 times 2, and see we would get a negative 14. We would get a negative number. So values in here will give you negative. Let me actually just write negative so we can tell. We'll give you a negative value, and that's what we don't want. So this won't be part of our domain. And now we check a number in here. Let's pick like x is 10. And let me write it over here so I have some more room. X is 10. If If I plug in x is 10 into here, I would get 3 times 12, and that'll give me a positive number. And that's good. That's what we want. We want a positive number. And so then our domain would be values up to and including -2 and values greater than or equal to 7. Now, there's a couple ways to write it. I like to use interval notation. Let me write the value over here. So I like to use this notation. So x goes from -infinity to -2. Since we include -2, we're going to use a bracket. And we skip union, start up again at 7, and go to infinity. This is typically what they'll use in more advanced textbooks and beyond, calculus and beyond. So I recommend start to get familiar with this, and it's actually easy. It's actually you'll find it's actually really easy to write and use. Okay, let's move on. So here we want to make again the denominator. We don't want to make the denominator we don't want to make this quantity 0 first because we can't divide by 0, and we don't want to make this quantity in here negative. So we have x squared minus x minus 30. It can't be negative, so we want it to be, greater than 0. So factoring this, we would get x minus 6 times x plus 5 is greater than 0. And so similar to like the one before, we want to again get products that will make this a positive number. And that will be when they're both positive or when they're both negative. If they're opposite sides, we're going to get a negative number, and that won't be part of our domain. So again, I advise making a number line at the zeros of these two factors. So x minus 6, if you solved for the 0, that would be 6. And then solve for the 0 of x plus 5, that would be -5. And then we test numbers in here, and here, and in here, and see what happens. So again, we can test like -10. If we put -10 into here, we would get -16 times a -5. And that will be a positive number. That's all good. So we want that. So this will be part of our domain. Now, since this number can't be 0, we're going to have an open circle here. We're not going to include -5. Now let's pick a number between -5 and 6, and let's just pick 0 because that's usually easy. Plug 0 into there, we get -6. 0 into there times 5, we get a negative number, which is what we don't want. So that won't be this region won't be part of our domain. You can probably guess what's going to happen. So we plug in x is 10 for this last part. Let me go over here. X is 10. So we get 4 times 15, and we would get a positive number. And again, we don't want to include 6 because we can't make this quantity equal to 0. And so our domain will be all the numbers less than -5 and greater than 6. Let me write it up here again using interval notation. So from -infinity to -5, put parentheses around 5 because I'm not going to include it. Union, start up at 6, parentheses around 6, but I'm not including it, and then up to infinity. All right, let's look at these last couple ones. At number 10, we have y is equal to the log of 2x minus 12. And for this, let's just remember that we can't take the logarithm of any numbers that are, negative or 0. So we want to basically make 2x minus 12 greater than 0 and solve this, and we get x is minus 12 plus 12, x is greater than 6. And that's it. Now 11, let's recall how our trig works. So if we're going to take the square root of a quantity, remember that we want it to be positive, or at least, or 0 at the very least. So let's look for values where tangent of x is greater than or equal to 0 on this interval, so from 0 to 2 pi. So let's actually just draw a graph of a number line going from 0 to 2 pi. And what I'm going to do is I'm just going to draw a sketch of the tangent function on this interval so you can see what's going on. The refresher in case you need it. So let me mark every let's mark pi on here, pi in the middle, 3 pi over 2, and pi over 2. Let's remember that the tangent of x is equal to the sine of x over the cosine of x. And if you were to graph it, it's going to have the tangent of x. Let me actually function has asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, and so forth. But we only care about this region. And it would basically approach this like this, asymptotically, like blowing up towards infinity. It would go through pi, go like that, and then go like this. Okay, so if we want the tangent of x to be at least 0, then that means that we will be talking about this part of the graph, this part of the graph, and this part. Well, only actually this part of only actually at this point at 2 pi. So our domain will be from 0 to pi over 2. And we'd skip, go from pi to 3 pi over 2. And technically, we would also include 2 pi. But I mean, that's just a technicality. So you could write it something like this. I would write it as x going from 0 to pi over 2, parentheses, start up again at pi, and go to, well, let me move this up. Pi, then go to 3 pi over 2. And you could also technically write pi if you wanted, but it's probably not necessary. It will kind of be redundant, but it'll be like that. All right, number 12, the last one. Okay, so we essentially don't want the denominator to be equal to 0, so we don't want the cosine of x to be equal to 0. So when is the cosine of x equal to 0? Well, since this is periodic, it doesn't give us a restriction of x. So starting, on the top of the unit circle, pi over 2, then 3 pi over 2, 5 pi over 2, 7 pi over 2. So every pi from pi over 2. So one way to write this, I would write, x cannot be pi over 2. It cannot be 3 pi over 2. It cannot be 5 pi over 2. And it cannot be 7 pi over 2. And one way that's common to write domains like this is just to put like a dot, dot, dot to show that that pattern continues. Sometimes I'll use like a k plus pi, over 2. That if you want to be a little more technical, but usually this is enough. But let's also remember that we can rotate clockwise. You can rotate clockwise or backwards. So let's make sure we put plus minus, because it'd be negative pi over 2, negative 3 pi over 2, negative 5 pi over 2, and negative 7 pi over 2, and so forth. But make sure you know your unit circle and your trig.